Hey guys, this is a review for Spiral 22. We're going to start off with some sequences and series. First thing we've got is 4n to the negative 1 and going from 2 to 6. I don't know any quick rules for a series that's some n to the negative 1, so what I might do is just do this one out. So this is 4 times 6. I don't know why I start with 6. I really should start with 2. So it's 4 times 2 to the negative 1. 2 to the negative 1 is a half, so that's 2. Then we're going to have 4 times 3 to the negative 1. And that's going to be 4 thirds. And then we're going to have 4 times 4 to the negative 1, which is 1. 4 times 5 to the negative 1, which is 4 fifths. And 4 times 6 to the negative 1, which is 4 sixths or 2 thirds. And I add these things up, so we've got 2 plus 1 is 3. 4 thirds plus 2 thirds is 6 thirds or 2. And then 4 fifths is kind of on its own. So that's going to be 5. Converting that to fifths, that'd be 25 fifths. Plus 4 fifths would be 29 over fifths as a final answer. For the second one, this one I probably don't want to actually do out. That's 17 different terms. So I've got to identify if there's anything I can do here to shorten this. In looking at this, I recognize that this is geometric. And I have a partial sum formula for geometric, which is my first term, which in this case happens to be 4, multiplied by 1 minus that common ratio, which in this case happens to be 0.2 to the n power. I don't know why I started to do this half in notation, so I'm going to erase that and just write this as a formula first. And then we're going to divide that by 1 minus the common ratio. So in this case, we've got first term 4, 1 minus 0.2 to the 17th power over 1 minus 0.2. When I do this out, in other words, when I do the calculation of this, we get 4 times 1 minus 0.2 to the 17, which is basically 4. I think it's funny that my calculator gave me the exact thing as 4 instead of going a little bit further. So it's like this part doesn't even matter. It's almost as though we're infinite. And we'd be dividing that by 0.8. 4 divided by 0.8 should be something slightly larger, which is going to be 5. As an alternative, if you want to leave it in this form, this would be totally acceptable. Now looking at this infinity thing, we've got to use our infinite series work. In this case, I've got an R value of 0.6. So 0.6 is less than 1. That makes me very happy because I can use my shortcut, which is the first term. The 1 minus r to the n part goes away, so it doesn't have to be there, and we get 1 minus r on the bottom. So 1.5, 1 minus 0.6 is 0.4. 1.5 divided by 0.4, and that's going to be 3.75. Next up, we've got some exponential graphs. We've got to deal with this by making this a little bit easier for us to work with. I'm going to try to make my exponent negative 1, 0, and 1. To make that exponent x minus 1 negative 1, I'm going to use 0 for x. And then to make it 0, I'm going to use 1 for x. And then to make that 1, I'll use 2 for x. When I plug those in, we get 1.5 times 2.5 to the negative 1. And that's going to be minus 6. 2.5 to the negative 1 is going to be 2/5. So we have 3 halves times 2/5. I get 3/5 minus 6, which is negative 5.4. We're going to repeat that for our next value, and in that case that's going to be 1. 2.5 to the 0 is going to be 1. 1.5 minus 6 is going to be negative 4.5. All right, then finally we got to plug in 2. 1.5 times 2.5, that's going to be 3 over 2 times 5 over 2. It's going to be 15 over 4 minus 6, which is 24 over 4. Looking at negative 9 over 4, which is negative 2 1/4. Okay, I'm going to plot these points. I'm going to include my asymptote, which is at negative 6. 1, 2, 3, 4, 5, 6. 0, negative 5.4. 1, negative 4.5. And 2, negative 2.25. My graph should look something like this. For the log function, what we're going to have to do is take a second to convert this to exponential. I'd like to remind us that this is log base 10. This is a common log if we don't see the logarithm there. And that in setting this up, we're going to convert this to exponential first. So I'm going to end up with y minus 2 is equal to negative log of x minus 5. And I'm going to get rid of that negative, so we got negative y plus 2 plus log. Convert this to exponential. 10 to the negative y plus 2 is equal to x minus 5. 10 to the negative y plus 2, big plus 5 is equal to x. Alright, I'm going to use my xy table, plugging in values for y. And I'm going to choose numbers that make this nice and easy to work with. So that'd be like negative, 1, 0, and 1 for the exponent. To get the exponent to be negative 1, this has got to be 3. To get the exponent to be 0, y has got to be 2. And to get the exponent to be 1, y has to be 1. Those are some pretty good points to work with in general. Okay, so we get 10 to the negative 1 plus 5 is going to be, I don't know why I put those outside. 10 to the negative 1 plus 5 is going to be 5.1. Then we're going to have 10 to the 0 is 1 plus 5 is 6. And when I plug 1 in for y, 10 to the 1, oh wow, 15, huh? Asymptote is going to be at 5. You could have also gotten that from the inside there. 1, 2, 3, 4, 5. Here's my vertical asymptote for my log. 5.1, comma 3. 6, comma 2. 6, 2. And 15, comma 1 would be somewhere over here. My graph would be an upside down log graph, which I might have predicted from that negative out front. Okay, moving on to writing an equation. I'm going to identify a few points. I've got 0, comma negative 2. And I've also, as far as another easily identifiable point, that looks like negative 1, negative 5. The next easy identifiable point would be negative 2, negative 11. But I only need 2 for this. First of all, I've got an asymptote at y equals 1. That means that k equals 1. So we're going to start out with the equation y equals ab to the x plus 1. Going to plug in my first point with a 0. Negative 2 is equal to a b to the 0 plus 1, which means negative 3 is equal to b to the 0 is 1. A times 1 is a. So I'm going to plug that in. Y equals negative 3, b to the x plus 1. And now plug in my second point. We used that one. We're going to use this one next. Negative 5 is equal to negative 3 b to the x plus 1. B to the negative 1 plus 1. Negative 6 is equal to negative 3b to the negative 1. Dividing by negative 3, we get 2 is equal to b to the negative 1. A negative 1 power is a reciprocal. That means that b equals a half. My final answer for this is y is equal to negative 3 times a half to the x, and then we had plus 1 at the end. Next up, we got some log basics. In terms of this, this is going to be calculator active again, so you need to make sure that you're showing an appropriate amount of work. Converting to logs, we're going to end up with log base 7 of 1 over 49 is equal to negative 2. That's based on recognizing the pattern of log base b of a is equal to e if and only if that same base to that exponent equals the thing inside the log. These two statements are equivalent. This is how you convert from one to the other. So this would be log base 9 of 3 is equal to 1/2 in a similar fashion. Evaluating each log, so we've got to do something like this. 2 to the question mark is equal to 2 to the 3x minus 4. You might notice that in this case, the question mark becomes 3x minus 4. Since those exponents are the same, that means that those are equal exponents. Log base 4 of 256 means 4 to the question mark is equal to 256. If I just plug things in, 4 squared is 16, 4 to the third is 64, 4 to the fourth is 256. So that means that's 4. Our answer is 4. Negative the natural log of 1. So negative the natural log of 1 is equal to question mark. We know this is really log base e. So this is e to some negative question mark is equal to 1. The only thing that I know is a power that puts things at 1 is going to be 0. So the negative natural log of 1 is going to be 0. In fact, any log of 1 will always be 0. We're going to do some solving. Here we're going to have to deal with trying to get these things into the same base, and if we can't, then we have to use logs. So I notice we've got 16 to the 3x minus 2, and I've got 64 to the x plus 11. Both of these are powers of 4 or powers of 2. It doesn't matter which base you use as long as you use the same one. I'm going to write 16 as 4 squared. Then we got to the 3x minus 2. 64 is 4 to the third to the x plus 11. I'm going to multiply my exponents, so we get 6x minus 4 on the left. And we've got 3x plus 33 on the right. We're able to do this because the only way an equation can be true if the two bases are equal is if the exponents are also equal. When solving this, we get 3x on the left and 37 on the right, which means that x is equal to 37 divided by 3. For the next one, I don't really know how to convert those into the same base because I've got an e here, and I've got other numbers that are not e. So I'm going to try to get this exponential piece by itself first, which means I'm going to start by dividing by 4. we get e to the 3x plus 1 is equal to 12. Now I'm going to convert this to logarithmic form. So that's log base e of 12 is equal to 3x plus 1. In other words, my natural log of 12 is equal to 3x plus 1. I'm going to leave this in exact form, not convert to decimals. So we subtract 1 from both sides, and I get the natural log of 12 minus 1 is equal to 3x. And then my final answer is that x is equal to the natural log of 12 minus 1 divided by 3. That 12 can't interact with either the negative 1 or the 3 because it's trapped inside its logarithm. So this is as exact an answer you can get. If you start trying to combine those things, then you move away from the right answer. Next up, we got some exponential and logarithmic models. We've got to write some models for these and use this to solve some problems. Okay, so we're talking about Miss Glynn, and she's holding a fundraiser. She starts with 50. I might just make a table to kind of make some sense of this. So time and money. Let's just use x and y. Why not? So on day 0, she's got 50. On day 1, she's got 85. The donations increase following continuous exponential growth model. So this is really specific in terms of the way that this is set up and the phrase continuous exponential growth. We're going to ignore that and just talk about an exponential model. And we know that should be y is equal to ab to the x plus k. We're going to use some reasonable thinking for this, and that reasonable thinking is that in real world models involving money, at some point she might have had less than the money she has now, and that might have been a $0 asymptote. I'm totally just making that up. I'm not going to give you something that is going to be this obtuse without some further explanation. And then looking at what's going on here, we're going to plug in our first point. So 50 is equal to a b to the 0. 50 is equal to a, and plug in our other point. That should be a 3, not a 1. So we've got 85 is equal to 50, b to the 3rd. Divide both sides by 50 and take the cube root. I get that b is equal to the cube root of 85 over 50, which you may or may not want to do out as a decimal. That might be a little bit easier for us to deal with and less gross looking. In terms of decimals, that is going to be, so we got 85 over 50, which is 1.7. The cube root of which is 1.1934. So we end up with an equation that's y is equal to 50 times 1.1934 to the x. After 30 days, this would be y is equal to 50, 1.1934 to the 30th power. So if I do that to the 30th times 50, in her account at that point, she's going to have $10,079.9695, which is pretty cool. We'll talk a little bit more about the continuous growth idea. Alright, so now we've got a fake element here, monkey aroundium, and this has a half-life of 13 years. We're going to write an equation to model the amount of monkey aroundium in your possession if you start with 238 milligrams of monkey aroundium. We can do this a couple ways. We can do this based on understanding what half-life means in terms of going from nothing, or we can start with an equation that we're used to. That equation, which you might recall from what we did in class this week, is going to be y is equal to the starting amount. In fact, we used a is equal to the starting amount, the principal, multiplied by 1/2, that's the half-life, and time divided by the half-life. As an alternative, we could build this equation based on some points. So at time 0, you have 238, and at time 13, you'd have half of this. So 238 cut in half would be 119. At time 26, the second half-life, you'd have this cut in half, which would be 59.5. You could keep doing that to get points and build an exponential equation, or you can work from the equation that we worked with in class. So my final equation would be a is equal to 238 times 1/2 to the t over 13. How much do we have in 22 years? I'm going to plug in 22. So we have 238 times 1/2 to the 22 over 13. And in looking at this, I'm going to do 1/2 to the 22 divided by 13, which is 0.309. You can tell when I have my phone calculator instead of a big calculator because it takes me longer to do the math. Times 238, which is going to be 73.6447 grams. I'm sorry, milligrams. How long until we only have 1 milligram of monkey aroundium? Okay, so that's going to go where my A value should be. And it's equal to 238 times 1/2 t over 13. I might start by dividing by 238. So we get 1 divided by 238, which is 0.0042. That's equal to 1/2 to the t over 13. Best way for us to do this is to convert this to log form, but you're not going to be able to get an exact answer, or you're not going to be able to get a decimal answer for that unless we do some other manipulation. And what I might do for that would be to convert this to 2 instead of 1/2. But it's still not going to make it better for most of our calculators. So what we're going to do is just convert this to log form as is. That's log base 1/2, and not something I love, 0.0042 is equal to t over 13. When I multiply both sides by 13, we get 13 multiplied by log base 1/2, 0.0042. And if I were to do this out as a decimal, if you're curious about the decimal value for this, so we have 13 times 0.0042 log divided by 0.5 log equals. It would be about 102.6 years. Which again, if you give me this answer, 100% correct, 102.64 years. If you do guess and check for this, you're not getting full credit. I need to see at minimum the conversion to log. Afterwards, if you wanted to do guess and check after I saw this conversion, that would be okay.